Okay, I'd like to talk a little bit about working memory, and this is material that you went through in chapter one, but because it comes back in the later chapter, and because it's so central to our course, I let you have slides without my over my lecture, and now I'm going back and delivering a lecture for that content. So most of what I'm saying should be review, but hopefully it will help you understand a little bit more. And you should expect some working memory questions coming up on future quizzes. So first of all, let me define either the term short-term memory or working memory. Let's start with short-term memory. Short-term memory is a somewhat old-fashioned word that has been updated by Alan Badley and others to the more contemporary working memory term. The construct, either short-term memory or working memory, refers to the information you are holding online in your head. So if you're listening to my words, you are holding some information online to understand me, that's working memory. If I read you a list of numbers like 5, 3, 7, 9, 2, and then I said, please repeat them back to me, and you said 5, 3, 7, 9, 2. You repeat them back, you're able to repeat them back because you held them in working memory. Actually, a few people looked at video clips for their first homework and saw people with damaged working memory, people who could hold very little information online. And in particular, the damage for some people involved passing information on to long-term memory. So let me back up a bit and just kind of repeat what I've said. Working memory is the memory that you are holding online as you think. Now, this is really very important. Working memory has a duration of probably 25 seconds. In other words, you can hold information in your mind for about 25 seconds. After that, it disappears. Now, when I say you can hold information in your mind for 20, 25, or 26 seconds, I know, of course, that you could keep repeating something in your mind theoretically for a day, forever. However, that's not what we mean. In everyday life, you get a piece of information in your mind, and you can hold it, and it degrades after a handful of seconds. So, to be very clear, if you drop your keys getting ready to go in the morning, and then you go back and you can't remember where you left your keys 5 minutes ago. 5 minutes ago is not working memory, it's long-term memory. Don't worry about that for now, but let me just tell you that the way we use short-term memory in the popular media is wrong. Short-term memory is your current the contents of your current consciousness, not what happened 5 minutes ago or this morning. So, one way to measure working memory, as I just discussed, is to read a list of digits or a list of letters and ask you to repeat them backwards. If we were to do that, we would discover that most people can hold about 7 items in their mind at once. 7 plus or minus 2. That we called Miller's magic number. Just to look back to chapter 1, thinking back to the cognitive revolution, why is it interesting that most people can hold about 7 items plus or minus 2? And the answer is that it demonstrates that the human mind has a capacity limit for memory, very much like a computer has a memory limit. In other words, if you had a purely behaviorist view, there's no reason why we would all show about the same capacity. However, if you talked to, let's say, a computer engineer and said, oh, it's interesting, the mind shows a capacity limit, they might say, well, of course it does. If it's an information processing system, it would have to have a capacity limit. So span tests are one way of measuring how many pieces of information you can hold in your head. And as we've said, most people can hold about 7. As we in later chapters, we'll get a little more technical about this, but for now, that's good enough. There's another thing to say about working memory. It turns out that it correlates, your ability to use working memory correlates in pretty interesting ways with overall cognitive capacity. So intelligence tests actually include tests of working memory. Now, this is real important. I drew this very simple schematic for you because I think it's going to be helpful. It doesn't show up in chapter 1, so let me just kind of unpack it a bit. First of all, as discussed, well, actually, you know what? Let me back up even more. Let me take a step back. Let me go back to Alan Baddeley's original thinking. So Alan Baddeley was a young psychological scientist interested in memory. When he was beginning his work, people talked about short-term memory, and they conceptualized short-term memory as a simple kind of holding space. So in other words, information somehow was taken in through the senses, and then there was some cognitive processing, and then information passed through short-term memory into long-term memory. And we're going to come back to that in more detail in a later chapter. But let me say right now what insight Baddeley had. It occurred to him when he was thinking about it that there are some kinds of memory tasks that are easy to do in a dual task situation. A dual task situation is when you're doing 2 tasks at once. And there are other kinds of memory tasks that are hard to do in a dual task situation. So let me give you an example. Imagine that you are reading a book. You're very interested in a specific novel you're reading. You're very engrossed in it. Could you turn on the radio and listen to National Public Radio, the 5 o'clock news at the same time? I think the answer is fairly obvious. You could not listen to the 5 o'clock news while you're reading a novel. However, could you switch the station to one of NPR's classical music stations and continue reading your novel? Here again, I think the answer is fairly obvious. It would be easy enough for you to listen to classical music, and note I did say classical, I didn't say folk music or what have you, while reading a book. Now let's consider another example. As you're driving down the highway, you're holding visual information in your mind. And now you have to be, otherwise you're going to drive off the road. So you're holding visual information in your mind. Could you, while you're doing that, visually image your kitchen? Suppose you're planning to tear out your kitchen cabinets and you're trying to figure out, what kind of design in my kitchen should I do? Could you call up a visual representation of your kitchen while you're driving? I'm going to suggest the answer is no. And that might not be obvious. If it's not obvious, I would suggest it's because it's so unnatural you don't do it. While you're driving, you don't try very hard to image other visual information in your mind. It's just too hard. So, what Baddeley observed was that we can do a visual memory task and a verbal memory task at the same time. In other words, we can hold verbal information, as in reading the book, in mind, um, potentially, but we can't hold another set of verbal information. Now let me put you back in the car for a minute. I should have given this example. Could you drive down the highway, visually imaging the road in front of you, while listening to your friend in the right-hand seat? The answer is obvious. It's easy to hold visual information online while processing speech, because visual and auditory information don't conflict. But again, you wouldn't listen to your friend while reading a book. It'd be one or the other. So again, Baddeley observes that in order to make sense of this idea of what used to be called short-term memory, we need to begin with the idea that there seem to be different subsystems, and some systems can work together, and some memory tasks are too difficult to do simultaneously. So we begin with this very simple model that I have on screen. In this model, the central executive is sort of the operator of working memory. The central executive, it's kind of a business metaphor, the person in charge, the memory structure in charge. And then Baddeley notes that there are two storage systems. For now, let's think about visual information storage and verbal information storage. This makes good sense. Going back to this question of the dual task, we can easily use the visual information over here, visual information space over here, and the verbal information space over here. What we can't do is two different verbal tasks or two different visual tasks simultaneously. They're separate systems. Think of these assistants, to use the book's term, kind of like pads of paper. You know, working memory needs to process information, and the system comes built with a little bit of storage space to process information. Let me give you a math problem to do in your head. What is 337 times 2? Let's take a minute and solve that problem. 337 times 2. Now, what I'd like you to do is think about how you solved it. Let me solve it out loud for you, and you probably did it either the same way or some other way, but let's think about it. 337 times 2. 300 times 2 equals 600. 30 times 2 equals 60. 7 times 2 equals 14. 300 plus 60 equals 360. 360 plus 14 equals 374. So I wanted to solve that out loud to give you a sense of how my mind needed to hold some information online as I stepped through the process. Even if you did that very quickly, maybe in just a couple steps, you had to hold some information online. Here's another example. Let me think of a sentence. While we were waiting for the boat, we stood on the dock and watched the lighthouse blink, and we thought about the fact that they'd left 10 hours ago and it was getting dark and a storm was rolling in. Not my best sentence. But if you followed that, and I was doing that spontaneously, so I can't really go back and say it all over again. But if you followed that, I intentionally began with a while we were doing such and such. We stood on the dock, and then I talked about what they were thinking about, and then I introduced the weather, and I tried to suggest that maybe there was a potential for some danger. So if you got all of that information, it's because you held the beginning part online. While we were standing at the dock, okay, they're standing at the dock, but you don't even know yet what the subject, what the kind of where the sentence is going. But you can follow that if you're an adult with reasonable working memory, because you're holding information while you're waiting for more. So we need these assistants to hold either verbal or visual information. We're going to give different names to these structures, this one and this one. But for now, I like to emphasize drawing pictures to help you think. The key point that I emphasize in this picture is that these two structures are separate. They're physically separate. Now, in reality, this is just a model. Working memory is a set of processes. I don't mean to imply that this is a brain region and this is a brain region. Rather, I mean to imply that working memory seems to be able to hold visual information separate from auditory information. Now, I think you probably got the gist of this from chapter 1, but again, I'm trying to review and really firm this up because this is going to come back in a big way. Now, this is just me showing you the working memory system holding cat information. Now, let's think about something really very important. Well, as humans, language is critical. And for most humans who hear language, language is coded preferentially by sound. Now, let me back up a bit. We're going to talk about the condition in which a person might be deaf toward the end of this chapter, but let's hold that. Let's talk about what we're going to call sort of or in the most typical developmental scenario. A child grows up and the child hears language and speaks language. Now, we know some people don't hear it or speak. They might use sign language or they might read. But for now, we're just thinking about the most typical developmental scenario. If I flash up this picture of a cat, you are very capable of holding a visual image of a cat in your mind. You certainly can. But now suppose I say, now here's a cat, and the cat sits on a chair. Well, you can mentally put a cat on a chair, and you could go from there. But what I want to suggest to you is that you don't. You don't think entirely in visual pictures. Most people don't. That would be really difficult. Instead, what you do is code it into sound. I flash up the picture of cat, and you mentally say cat in your mind. Look carefully at the picture from the book that reminds you that you have both an inner voice and an inner ear. You can subvocally produce speech. You can subvocally hear speech. You can say cat over and over in your mind, and you can hear yourself say it over and over in your mind. And of course, when I say hear, I really mean to sort of put this in air quotes, because clearly you're not hearing it. You're mentally representing sound information. Cat has 3 sounds. K, at. I flash up the picture and you mentally encode the word. I could draw a picture on the board. I could draw a picture of an apple. You would mentally say apple. Imagine if I drew a picture of an apple as opposed to writing out the word apple, A-P-P-L-E. In either scenario, you would very quickly mentally encode it over here. So let's say I flash a picture. The central executive has to send some information over to here for it to be encoded by sound. So again, that's what we meant by subvocalizing. Now, this was in the book, covered in the book, you've gone through it, but it's not easy at all. So here's the scenario I want you to imagine. Imagine that we're in a face-to-face class setting, and I flash up letters, either one at a time, or in a series, one after the other, or all at once in some sort of a matrix. I want you to imagine that I'm asking you to remember as many letters as you can. That would be a working memory task. Assuming I asked you to remember them for like several seconds, that would be working memory. As a thought experiment for a second, let's just look at the letters I have on the slide. B, F, M, V, R, K, L. Suppose I read them one at a time, and you knew that in a second you were going to be quizzed. So let me give you another one. I'm going to read a list, and then in 5 seconds, I'm going to point to you and ask you to write them down. Let's do that as a kind of imaginary classroom experiment. Here goes. L, N, T, Q, R, B, E, X, C. Now please write down as many letters as you can. Now that was an imaginary class experiment. And the thing I'd like to point out is what you probably did is you probably rehearsed them over and over in your mind. B, BF, BFM, BFMV, BFMVR. Each time I introduced a new letter, you cycled through and repeated it. That's not such a bad strategy. There are other strategies, but if I'm reading letters fairly quickly, you'd be really hard pressed. There are other strategies that would be better if you had more time. So, for example, if this was a long-term memory task and I let you study the list for 10 minutes, maybe you'd make a sentence. Best friends make very, I don't know, something. Maybe you make a sentence. Well, that's good. That's great if you have a few minutes. But in the example I just gave you, you don't have a few minutes. It's a working memory task. So you rehearse. And then the question I wanted you to think about was the kind of mistake you are likely to make. The sort of obvious answer, if you do not think about how cognition works, is to think that you might make a visual sort of mistake. So V kind of looks like a W. Maybe you'll mistake V for W. E kind of looks like an F. So maybe, in fact, an E looks very much like an F. It's an F minus the base, right? So if you made a visual mistake, you might forget that I said E and replace it in your memory. Your mistake might be F. Now think about it. The letter E is flashed over here. Why would it make sense that you'd mistake it for an F? Well, it makes sense if you think that working memory has kind of a bias toward visual imagery, but what I said before is it doesn't. I flash up the E, and your central executive sends it over for you to subvocalize it. E, you say in your mind. So if you're going to make a mistake, you're actually going to make a sound-alike mistake. E sounds like C. It looks nothing like a C, but it sounds like a C. Sure enough, if you make a mistake on E, it's much more likely to be a sound-alike mistake than a look-alike mistake. That's a really important point that you do well to think some about. Draw this picture and think it through. This is not obvious. A lot of cognition sounds obvious when you hear the faculty talking. It's I'm stepping through you, and it's easy to sit back and say, "Oh, yep, that makes sense. Got it, I got it." And actually, it's quite a bit less intuitive than you might think. And so if you just kind of nod your head and say, "Oh, he's making sense," you might easily be confused about this later. Now, let's move on. In working memory tasks, people have done lots of different kinds of working memory tasks. Let me give you the example of a working memory task in which I read a list of words and ask you to remember them. So I'm going to do that. Let's do a virtual kind of imaginary couple classroom demonstrations. So let's imagine you're sitting in the classroom. I'm going to read you a list of words, and then I'm going to say, I'll stop, and then in a few seconds I'll say, write down as many as you can. Let's give it a go. Here comes. Cat, fox, hen, dog, cow, bull, finch. Go. Okay, now look and see how many you got. And I'm going to confess to you that I made those words up as I was going, which was a bad way to go because I can't actually see if you got them all right. But I read 7 or 8 words, and I'll bet you did pretty well. I bet you got them all right. Now, I'm going to read you a second list, and we're going to do the same thing. I'm going to read a second list, then I'm going to give you a second and say, write them down. Here goes. Hippopotamus, alligator, elephant, giraffe. Let's tell you what, I'm going to start over. Give me 1 minute. I'm going to start over. Okay. As I was doing that, it suddenly occurred to me I should write out a list and do this a little more formally, just as I would if I was in front of a class. So let me do that. Let me ask you to indulge me and back up, and let's do it again. So take out a piece of paper. I'm going to read 2 different lists, one at a time, and we're going to do a working memory task. So I'm going to read the list, give you a 2 or 3 seconds, and then say, now write down all the words that you can remember. Let's try it. This will be a real working memory task. Okay, here comes the first list. I'll read about 1 word per second or so. Ready, begin. Ingredient, elephant, computer, dictionary, hypnotist, library, celebration, memory, situation, necessity. Please write down as many words as you can remember. I'm going to read the list and let's see how you did. Ingredient, elephant, computer, dictionary, hypnotist, celebration, memory, necessity. It's very conceivable to me that you might get all 10. Or maybe you missed a few. That 10 isn't too hard with rehearsal. But on the other hand, you may not have gotten all 10. Let's try our second list. Okay? Here goes. Pen, knife, hat, bull, meat, dress, shoe, cup, sign, rope. Okay, please write down as many as you can. I'm going to read the list and let's see how you did. Pen, knife, hat, bull, meat, dress, shoe, cup, sign, rope. Now, this was a demonstration. For a real working memory task, we'd want to make sure those words were equivalent on not on complexity, let me back up, on frequency. But what was different between the first list and the second list? What you might have noticed is the first list had long words. Most words had 3 syllables, or possibly 4. A couple had 4 syllables. So my question that I just tried to give you sort of a crude demonstration of, my question is this: which list should be harder and why? If you understand working memory after reading chapter 1, you might be able to get this. Which list should be harder to remember and why? Another way of asking that is, which list would you be more likely to remember more words on, or less words? The answer is, you would be more likely to remember more words on the short word list as compared to the long word list. But in cognition, the why is the important question. That's the phenomenon. We could easily demonstrate that people will do better on average with a list of short words as compared with a list of long words. That is called the word length effect. That will come back. You will need to know it. The word length effect reminds us that it's more difficult to remember a list of short words than a list of long words. But that factoid, remembering what the definition of the word length effect, doesn't really get you a lot of points. For points, you should be able to say why. So, and sorry, when I take a pause and I restart it, it seems to jump me back to the beginning. So what I just said is this: the sort of the 1 point understanding is what is the word length effect. It's easier to remember a list of short words as compared to a list of long words. However, for the full 5-point level understanding, you should be able to say, and even better, to draw a picture to demonstrate why we show the word length effect. Look very carefully at your book's drawing of the articulatory rehearsal loop. The first thing you want to kind of think about is it has a capacity limit. I would draw a line like this. And then I draw a little arrow that stands for rehearsal. So what does that mean? It means that short words are going to get better rehearsal than long words. So let's just think about this. Pen, knife, hat. Pen, knife, hat, bull. Pen, knife, hat, bull, meat. Pen, knife, bull, hat, meat, dress. Doesn't it seem clear that you're able to cycle through one syllable words much more quickly than 3 or 4 syllable words? Ingredient, ingredient elephant computer dictionary, ingredient elephant computer dictionary hypnotist, and on and on. The longer words literally take up more space in the buffer for sound information here. And then when you cycle through them, when you rehearse them, they literally get less attention, less time spent. Because in the case of the short words, they're one syllable. One syllable is much more quickly cycled through than 4 syllables. So we get our word length effect. Let me also say that this same explanation makes perfect sense for the sound-alike effect. We make sound-alike errors because we're looping through the sounds, and as we loop through sounds, 2 sounds like B, C, E, they almost interfere with each other because they're so close acoustically. Okay, so we've just explained what the word length effect is. I spent 10 minutes on this, and I did that because I know this is more difficult than it seems at first pass. And I know that many students will be lulled into a feeling that this isn't difficult at all. And then when they get to quizzes, it'll be easy to show that for some students it is difficult. I hope you will step through this, draw pictures, write out information, take notes on your own. Now, so let's review a few things that we've said. We've said that the working memory system separates visual information from sound information. We've said that you can't do 2 different sound tasks at once, but you can do a visual task and a sound task at the same time. We've talked about how sound information can be rehearsed to hold information online. We're very, very good at that. We're very good at manipulating sound information in our minds, assuming again that we're talking about sort of typical development in which language is preferentially processed by sound. Now, Alan Baddeley and others wanted to provide evidence that visual and sound information is separate. And they wanted to understand if their model of working memory was, I want to say, moving toward correct. When in cognition, when models begin, they're probably not completely finished, but are we moving toward a better model? And so they did all kinds of interesting experiments. Here is a dual task experiment. And when we talk about dual task, we mean doing 2 things at once. They did a dual task experiment involving concurrent articulation. Now, what is a concurrent articulation? And as I'm talking, I'm fully aware that this is mostly a review for you. You read this in chapter 1. So for those of you who read it really well, please bear with me because this is worth hearing. Concurrent articulation is when you are asked to repeat the same word over and over. A simple word or a simple sound, like the. So, now, what does a simple repetition of a sound do? Well, It's interesting to think about. One thing it does is takes up your articulatory rehearsal loop. In other words, while you're saying a word over and over in your mind, the, your articulatory rehearsal loop has a job to do. You're using it. So what's the consequence for using it? That means it's not available for whatever the other task is. Remember, this is a dual task. You're doing two things at once. It's not available for the other task. Now, let's go back to that working memory task where we just looked at a list of long words and a list of short words. What would be the consequence of concurrent articulation? If you are really completely 100% following my lecture so far, you might have an insight. And I didn't mean that in a snarky way of implying that if you don't get it, that you're not following it. I didn't mean that at all. Rather, what I'm saying is this is really quite difficult. And if I'm asking this question and you're a little bit sketchy, you're a little bit confused, then really you're right where I would expect. I expect this to be confusing. I think you're going to want to listen to my lecture and go back and do the reading, and then possibly even come back to this lecture. Let's restate the question. What is the effect of concurrent articulation on those two tasks in which we showed a word length effect? Well, to answer that, let's say again why we show a word length effect. And then let's ask how concurrent articulation affects that task. So we show a word length effect because it is easier to rehearse a list of short words as compared to a list of long words. So the short words literally get more rehearsal. They get more repetition. They get more sort of attention to each word. However, how does concurrent articulation change that fact? Well, in concurrent articulation, neither list gets any rehearsal. If you're doing a really honest job with concurrent articulation, you can't use rehearsal for the word list. Simply put, your rehearsal mechanism is taken out of the task because you've been given a dual task. Your concurrent articulation mechanism has a job to do. So the consequence is that the word length effect will be reduced or it will go away altogether. There'll be no notable difference between your performance in the long list versus your performance in the short list. And again, I can't say enough that you don't want to just listen to me and kind of nod your head. You want to really draw pictures and illustrate this yourself. Really kind of work it out on paper. Now, just to be clear, nobody does better at anything with concurrent articulation. Giving you a dual task has to impair your working memory a bit. It's not helpful to have to do something else, sort of do something else while you're remembering something. However, it's going to have a more negative impact on the short list, which benefited the most from rehearsal. So again, the word length effect will be reduced. So too will the sound-alike effect. Later in the semester, we'll give the sound-alike effect another name. We'll call it, what will we call it? The phonological similarity effect. Don't worry about that for now. Just really think about what the sound-alike effect is, and you should be clear that it will be reduced for during concurrent articulation. Don't worry right now about the jargon phonological similarity effect. I do want you to remember the word length effect because I don't have any simpler way to state that. Okay. I think this next slide should be clear now. And clear now. Now we get to a hard question. I asked you to think about this. I gave you this to think about in your homework, which, by the way, a lot of people put a great effort into, and I really think that will pay off for you. When I give you homework, sometimes I'll give you homework that you have a lot of lecture support for, and sometimes I'll give you homework and kind of let you let you off on your own and do your best, and then I'll come back and teach over what I thought was difficult. So this is a case where I let you off on your own, and now I'm sort of follow up teaching. So imagine I gave you a list of shapes. Now this is visual presentation. I flash a shape up on the screen and ask you to remember it. So let's begin with simple shapes. What are you going to do if I flash up triangle, square, circle, the actual pictures of shapes? Well, your introspective intuition is probably sufficient here. What you would do, most likely, is verbally encode the shapes mentally. Verbally, you would encode them mentally. Um, uh, Again, I want to keep emphasizing, right now I'm talking about the most typical kind of cognitive development. If a person was hearing impaired, they would use different processes, but this is how the mind would preferentially process the shapes given the use of a spoken language. So for the simple shapes, you would encode them linguistically. You'd encode them into words. So for that reason, that task, encoding simple shapes in a working memory task, should be impaired by concurrent articulation. Why? Well, again, now this should probably be pretty clear. It would be impaired because you're simply going to be able to repeat the words, triangle. You're not going to be able to repeat them while you're doing concurrent articulation. But now let's look at this complex shape. How would you be impacted from memory for complex shapes? Well, first of all, let's begin by saying I drew a complicated complex shape. I didn't have to draw such a complicated one. But what I hope you can see is that you can't encode that linguistically very easily. Now, okay, maybe you're very good at visual imagery. Oh, that's kind of like a man with a big nose with a funny hat on and he's got a big gaping mouth, or it's kind of a cartoon, or maybe it's a lampshade with a moon covering a moon and maybe a whistle behind it. It's certainly true that I can sit here and I can make up kind of a language-based story for that complex shape. But clearly, I can't give it an easy, automatic name that's going to be helpful. So if you flashed up complex shapes, say 1 per second for a working memory task, I would not be able to use language in any easy way. My central executive would probably rely on the visual. Let's go back to that visual shape, right? The visual assistant to hold shapes. So, simply put, concurrent articulation would affect this simple shape task quite a lot. It probably wouldn't affect this task at all. Now again, the complex shape task is hard, no question. But the point for us here is that it would not be impaired so much by concurrent articulation. Why? Well, the complex shape task doesn't really use the rehearsal mechanism. I just wanted to include this book's nice picture. This next slide just shows you the sound alike task that we stepped through. This is an old task. It was done by someone. They flashed a matrix of letters. And just to review, if you were to forget this F and you were to remember a letter in its place, would you be more likely to remember an N or an E? And if you have followed me through this lecture, the answer should be obvious. You'd be much more likely to misremember N in place of F rather than E. Why? Because N has a lot of sound overlap with F. F, N. They both begin with that sort of short E sound. On the other hand, the E is a close look-alike for that F. But people don't make look-alike mistakes. They make sound-alike mistakes. People have done a lot of work looking at neuropsychology, cases of brain damage. I've used the term cognitive neuroscience, and the book defines it. The way I would define cognitive neuroscience for you is trying to understand how cognition happens in the brain. Very interesting, the last little section in the end of the chapter about anarthia. People who have speech production problems, do they still show the same patterns of errors? The answer is yes. They make sound-alike mistakes. One thing it teaches us is that sound-alike mistake is happening at a more basic kind of language level, not at the motor level. Remember, a sort of a theme of the course is that cognition happens at stages, happens in stages. And this sound-alike error is happening at a very language-based stage, not at a motor production stage. Picture from the text. I think it's a fascinating example from the text about the kinds of errors the kind of things that similarities for deaf people who sign, people who use ASL, for example, deaf people who use ASL. What's the analogy in ASL for sounds? A word. So if you're a speaking, hearing person, cat is comprised of sounds. For deaf people, the symbol, the ASL symbol for cat consists of pieces of hand movement. And I'm sorry, I jumped off that slide. And sure enough, people who use sign show some interesting overlapping patterns of where you can see that signs are comprised of sort of, I want to call it pieces of a hand gesture. So let's say a piece of a hand gesture is analogous to a sound in a word. If this was a developmental class, I might talk about really interesting evidence that children who are deaf and learning sign babble with pieces of sign. So hearing babies babble by repeating sounds over another, like ba, 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 ba. And it seems to be that they're practicing the sounds of their language. As it turns out, children who are growing up deaf do something very similar. So review that really interesting evidence for how we can understand the language system by looking at the case of deafness. I try to incorporate, you'll see this a lot in chapter 2, I try to incorporate cases in which we look at either brain damage, maybe for an accident, or a developmental case of a piece of damage. For example, developmental prosopagnosia, which you're going to get in this chapter 2. Similarly, the case of a deaf person or a blind person provides us a really interesting window into thinking about what aspects of cognition are performed a little bit differently and what aspects are similar. So let me stop there. This lecture contained lots of difficult material. And again, I want to emphasize for students that I really hope as you go through these lectures that you're taking notes and really challenging yourself. Go back to the homework and look back at those questions. Really make sure that you're abstracting out the important information. On the other homework questions where I asked you about Donders or about Tolman, Garcia Colling, history of behaviorism, cognitive revolution, if you should have written really clear, fleshed out examples, really clear, fleshed out answers, which again, most people did. But remember, for the exam, I really expect you to know this. And so if you felt like you were shaky, go back and watch the videos again. Consider the homework as one piece of a guide to what I want you to know. You're also going to see that I'm about to load, either probably this evening, a couple sort of chapter outlines. Not an outline of the content of the chapter, an outline of what I covered and how I want you to think about it. So you would look at my outline and make sure that you have notes. Take my outline as if it were kind of a keyword subtopic list. Not notes that you can study from because there's not enough information on them, but more like key topics. Oh, you see a key topic and make sure that you have notes and understanding on it. Okay, and now I'm going to sign off.